now I'm going to talk about the sort of, as I said, nuts and bolts, and try to convince you that it's not hard. Actually, I know I think it's hard. Convince you that these are hard measurements, the measurements of atmospheric constituents, and especially the constituents in the troposphere. So, first of all, I mentioned the CEOS Earth Observer Catalog, maybe I didn't mention, but anyway, it lists 44 active surface measurement missions. There are 6 that are currently flying with the goal of measuring the atmosphere, some property of the atmosphere, not always the constituents, but some property. And they're mostly air quality, greenhouse gas, meteorology applications. And most of them use nadir observation geometry, right? You know that means you're looking down at the Earth. There are other kinds of measurements you can make. I'll mention some of them later. But basically, the satellite is at, low Earth orbit, and it's looking down. It's receiving light from below in the same way that you would if you were actually measuring the surface. But the goal here is not to measure the surface, but to measure the composition of the atmosphere under the satellite. And the way you do that is by looking at Rayleigh scattered sunlight. First time I heard about this, I thought it was just completely absurd. Because if you studied Rayleigh scattering in physics, you know that Rayleigh cross-sections are 12 orders of magnitude smaller than anything else. They're just absurdly small. And yet what people are doing is they are looking, of course the atmosphere scatters sunlight, that's why it's blue, that's why the sky is blue. It scatters light, and so there is this scattered light that the satellite can measure. And the way the composition is determined is molecules of absorbing gases, absorbing molecules that are in the path of that light absorb some of the light. So the satellite actually measures a spectrum. The instrument that on the satellite measures a spectrum of the molecules that are absorbing some of this ridiculously weak Rayleigh scattering out of the sunlight. So that's how most atmospheric measurements are made. And believe it or not. So I'll also give you a tiny piece of history and point out the first atmospheric observer mission that was launched, and it was Skiamaki. Probably heard that name. If you haven't, it means Scanning Imaging Absorption Spectrometer for Atmospheric Cartography. Actually, the person who made up that name, and it sounds as ridiculous now as it did when it was launched. And now I embarrass myself. Don't forget it. Thank you. No, too old. Anyway, Skiamaki is a dispersive spectrometer, and it's on NVSat. And this is NVSat here. This is not Skiamaki. Skiamaki is this little cube up here in the corner of NVSat. It has a whole bunch of other instruments on it, and it's sort of the scale. NVSat is 8 tons and around 10 meters long. And Skiamaki is a little over 200 kilos, and it consumes 155 watts. And you should remember those numbers for comparison with what I'm going to talk about shortly. And it costs 2.5 billion euros. That's Skiamaki, that's not NVSat. That's just the instrument. And it took something like 15 years to develop that instrument and tune it. Well, they were the first, so you expect that kind of gestation is necessary. But what I'm trying to say here is that this is an enormously big satellite, and it's typical of, there were a few that were launched of that size in this time period, late 90s, early 2000s. And that's just not possible. Put a 10-ton satellite into low Earth orbit There are some rockets, of course, that will do it, but they're getting fewer and fewer. And there's good reason for that. There's no need. Anyway, if you look up the Skiomaki website and you get yeah, there it is. You will get this information, which is what the designers of Skiomaki said they wanted to do. And basically they wanted to do everything having to do with the atmosphere. And they had all kinds of viewing modes. In other words, in addition to nadir looking down, they looked at the limb of the atmosphere, that's sort of grazing. They looked through the atmosphere of the sun, that's occultation. And they had all kinds of moving parts and scanning mirrors and stuff. And it is a miracle that this is actually still working. And the goals are down there, you can read them, and they said they were going to retrieve this laundry list of molecules and properties of the atmosphere. And they have done some. They have done some. They certainly haven't done all of them, but they have been successful at measuring some, and the most successful measurements, I guess, are from NO2. Our NO2 columns, and here is a Skiomaki NO2. They also measure SO2, CO. You know, I shouldn't. They measure a lot of stuff. They just don't measure as much as they said they would. Anyway, this is an example of a 6-month average of Skiomaki measurements. Low Earth orbit gives you around 16 orbits per day. And so you add those all up and average them for 6 months, and you get a picture that looks like this. This is tropospheric NO2, and it's tropospheric, it's not stratospheric. There's NO2 in the stratosphere, but they extracted that. And it is a column measurement, so it's, don't know if you can read this, but anyway, it's the number of NO2 molecules in a column, the 1 square centimeter cross-section. In the whole atmosphere. No, sorry, not in the whole atmosphere. In the troposphere, from the tropopause down. And so, you know, you can see, yes, there's a lot of NO2 that comes from automobiles and factories and things like that. So, oh, and that's Randall Martin, by the way, is Alexi did that work. And it reveals a lot of things, but it doesn't. Well, again, this is the state of the art in the middle of the last decade. This is how well you could do.
So this picture then is down to square centimeter resolution?
No.
For this color?
No. The resolution per pixel here is, it's on the order of 10 kilometers. I can't remember exactly, but it's on the resolution is on the order of 10 kilometers, okay?
It's normalized.
So when it's just that the units are quoted in columns of square centimeter columns. So, you know, you make a measurement that has a resolution of 10 kilometers, and you say, okay, how many molecules is there in a square centimeter?
Okay.
Yeah.
There's some black outline of the continents that was superimposed, right?
That's superimposed.
Okay, I was wondering what black outline
Yeah,
was.
yeah, you always have to plot these things on a map. Although for this, you know, you could probably know where they are without the map.
Well, from here it looked a bit like it could have been a series of red dots on all the edges. I was trying to figure it out.
Yeah, I see. No, those are continents. Yeah.
I was wondering if there was any effort to normalize this based on population density.
Oh, you can, listen, these things have been analyzed every which way. Yeah. These are simply the raw retrievals that Randall did. And so, yeah, then depending on your speciality, you take this and go crazy. And also, you know, finger pointing at who's producing the most NOx and transboundary transport and all kinds of things come from this